Hello there, Mr. Sutton here with the AB Calculus 3-9 Extra Practice Number 1 solutions on tangent lines and higher order derivatives. For this problem, they want the equation of the tangent line of this graph at 1, 5. So we've already got the point for the tangent line. We just need the slope of this function at this point. So let's find dy over dx. To get that, we will need the quotient rule here. So let me set up my box and ribbon to find u prime v minus uv prime over v squared. So I have my numerator of 2x plus 3, denominator of 3x minus 2, and their derivatives, which are 2 and 3 respectively. Now I just need to find the actual value of the derivative at 1, 5. I don't need to know the formula for the second derivative, or for the first derivative rather. So I'm just going to plug 1, 5 in here inside the box. So at x equals 1, and actually I don't even need to know the y value because I only have x's for plugins here. So at x equals 1, I've got basically 2 plus 3, which is 5. And then this is going to be 3 minus 2, which is 1. Down here we just have the constants 2 and 3, which are still 2 and 3. Using the ribbon to put it all back together, we've got 2 times 1 minus 5 times 3. All over 1 squared. Well, this is just 2 minus 15 over 1, so that's negative 13. Putting it into point slope now, I can write y minus the y value 5 equals my slope that I just found of negative 13 times x minus the x value they gave us of 1. And that doesn't match any of the answer choices, so we're going to have to put this in standard form. To do that, I'm going to start by distributing this negative 13 over on the right side, so negative 13x plus 13. And now, to get standard form, I have to move all the variables over to the left side and non-variables to the right side. So I've got a 13x that's coming over to the left. I have a y that's already there, so I'll do plus y. This minus 5 has to get added over to the right to be with the 13, so that's going to be 18 over there. And let's see, that's going to give us answer choice B. For this problem, they want the equation of the tangent line for y equals x plus cosine of x at 0, 1. So I already have a point to plug into point slope. I just need the derivative of this function at 0, 1. So let me do y prime here. That's going to be 1 plus derivative of cosine, which is negative sine of x. And now let's see, let's plug in 0 for that, for the x value. So that's 1 minus sine of 0. Well, sine of 0 is just 0, so this is just 1. Plug in all this in point slope now. We've got y minus the y value 1 equals our slope that we just found, which is also 1, times x minus the x value 0. Well, I can write this if I distribute the 1 as x, and then if I add the 1 over here plus 1, and that allows me to match answer choice B. For this problem, we have this line x plus y equals k, where k is a constant, tangent to the graph of this parabola here. We want to know the value of k. Well, if we're trying to figure out where this thing is tangent to this thing, it'd be helpful to know the derivatives of these things. So let's get the slope of this line, which we can very easily get by just putting it in y equals mx plus b form. So I'll rewrite this as y equals negative x plus k, which means we just have a derivative of negative 1. Okay, now how about the derivative of the original graph here? So this is going to be 2x plus 3 that y prime equals. And we want to know where this y prime and this y prime actually match up, at what x value. Because if we know the x value, we can find the y value, and if we know the y value and the x value, we have enough information to plug in for these and figure out that mystery k value. So setting negative 1 and 2x plus 3 equal to each other, subtract 3, divide by 2, we've got negative 2 for the x value. Now where can I plug this back in to get the y value? Well, it would be safest to do it in the original function, and in fact that's the only choice we have because your tangent line has a k that we don't really know the value of yet. So plugging negative 2 in here, I've got negative 2 squared plus 3 times negative 2 plus 1. That's going to be 4 minus 6, which is negative 2, plus 1 is negative 1. Plugging negative 2 for x and negative 1 for y into this tangent line equation now, we see that k has a value of -3. So that's choice A. For this problem, we have some differentiable function, and here's a function value at 2 and the derivative at 2. And then g is defined as this original f function times x. We want the equation of the tangent line for g at the point where x equals 2. All right, so if I want a tangent line, I need an x value, a y value, and a slope. I have an x value here. It's 2. Let's get the y value next. So in order to get the y value, I need to plug 2 into the g function, since that's what we're looking for the tangent line for. So that's going to be 2 times f of 2. Well, f of 2, they actually gave us up here. That's 3. So this is 2 times 3, which gives us a y value of 6. So we're going to end up with y minus 6 and x minus 2 in the equation, which at least eliminates answer choices A and B. All right, now we need to know g prime at x equals 2. Let's start by getting g prime in general. For that, we're going to use the product rule, u prime v plus uv prime. And for that, I'm going to use my box and ribbon. So I have in the numerator here the original factors, which are going to be x and f of x. Down below, I've got the derivatives of those, which are 1 and f prime of x. So let's actually plug in the x value to all of this stuff. So if I do that, we have x turning into a 2. F of 2 up here we saw is 3. They gave us that information. 1 is still the constant 1. And f prime of 2 now, here's where this comes in handy. This is going to be -5. Using the ribbon to put that all back together, I've got 1 times 3 times 2, or rather plus 2 times -5. So this is 3 minus 10, which is -7. And now I have enough information to write my tangent line. So I have y minus that y value of 6 equaling my slope of -7 times x minus the x value of 2 that they gave us. And that's going to match answer choice D. On this problem, we're given the function 2x plus 1 to the 4th, and we want the 4th derivative of f of x at x equals 0. All right, this is going to be fun. So we need to take 4 derivatives on this one. There isn't really a faster way to do it other than using the chain rule, because we don't really want to multiply all this out. So let's see here. I'm going to have 4 times something to the 3rd, so 4 times 2x plus 1 to the 3rd, times the tail of 2, the derivative of this 2x plus 1 inner function here. So that's really 8 2x plus 1 to the 3rd power, because I've got that 2 for a tail in there. All right, so let me go on to my 3rd derivative now, and I am going to simplify as I go just to make it easier so I don't have a bunch of tails hanging around. So now we need f double prime. That's going to be, let's see, 24 times 2x plus 1 to the 2nd power times the tail of 2, which we can now turn that 24 into a 48. And yes, there's a little bit of a pattern here. F triple prime, now we're going to have 96 times 2x plus 1 times the tail of 2. So I can rewrite this now, and I'm actually just going to go for broke here and just distribute this out. So this is going to be, let's see, 96 times 2 is 192. Distributing out 192, I've got, this is going to be 384 plus 192. And now for my 4th derivative, I just take the derivative of this stuff, which is just 384. And that's going to give me answer choice E. Now I can take the extra step of plugging 0 into there, but again, this is a constant function, so that's not going to change anything. So choice E, any way you slice it. For this free response problem, we're given this crazy looking curve here, and they want us to show that the derivative equals this also crazy looking function. Okay, so the good news is we know what this is supposed to turn into. We just need to get from here to here. So to do this, we're going to use implicit differentiation because it's mighty tough to isolate those y's. So let me start on the left side. We've got 3 times 2, which is 6, y squared, times a dy over dx tail. This next expression is going to require the product rule. So I've got factors of 6x squared and y, and their derivatives are 12x and dy over dx. Multiplying that out with the ribbon, I've got 12xy that I'm adding in here now, plus 6x squared dy over dx. Moving on to the next term, this is going to be negative 24x, and then this last one is going to be 6 dy over dx, equaling the derivative of 1, which is 0. Now I have to isolate dy over dx. So let me keep the dy over dx stuff on the left, move everything else to the right. So on the left, I've got 6y squared dy over dx. I've also got the 6x squared dy over dx. And finally, the 6 dy over dx. Moving over to the right, I have to subtract this 12xy, and I have to add the 24x. So I've got 24x minus 12xy. And the reason I'm writing it in this order is I look up at my answer here that I'm supposed to get, and that seems to be the order that things are going in, an x minus an xy. I'm just kind of making this up as I go, but I think that's going to give me what I want. All right, next, let me factor out a dy over dx from the left side. That leaves me with 6y squared plus 6x squared plus 6 inside. And I'm now going to divide by all of this stuff. Now, when I do that, I end up with this, which clearly does not match this. But the reason for that is that I can reduce all of this by 6. So reducing the numerator by 6, I've got 4x minus 2xy downstairs, and you'll notice I switched the positions of the x and the y here. I've got now x squared plus y squared plus 1. And that matches what we have up here exactly, so I've done what they asked. On this problem, we want the equation of each horizontal tangent line to the curve, so our answers should all be in the form of y equals some constant if we have a horizontal line. To start this off, though, horizontal means that our slope, our dy over dx, must equal 0. So we basically have to figure out where this whole thing equals 0. And this is going to equal 0 wherever the numerator equals 0 and the denominator does not. So let's set the numerator equal to 0. So let's see here. If I want to solve this, I can start by factoring out a 2x from each of these terms. That leaves me with a 2 minus y inside the parentheses. And that gives me the solutions of x equals 0 for this 2x here, and also y equals 2. Now let me just double check real quick here. If I plug either of these in, will that give me 0 in the denominator? Well, if I plug in 0 for x, that won't necessarily give me 0 in the denominator. In fact, it can't, because this y squared can't be negative, and we have another positive number here. So we're safe on that. And if we plug in the 2 for y squared, we're also safe there. There's actually no way that this numerator can come out to 0. So either of these is going to give us 0 in the whole fraction. Okay, so let's check the case where x equals 0, because we actually need the y value back for that. So if x equals 0, what does our original equation look like here? So plugging in 0 for x, we're going to have still 2y cubed plus, well, this whole next term is going to get zeroed out, minus this whole next term is going to get zeroed out, plus 6y is still going to be around, and that whole thing is still going to equal 1. Now this is going to be kind of annoying to try to do algebraically. This is a calculator question, so we're going to plug this in the calculator. So here I am on the calculator. I've plugged the left side of my equation into my y1, and notice I'm using x instead of y because that's what my calculator likes in order to graph things. And I've got 1, the right side of my equation, is y2. Let me zoom 6 this thing just to see what I'm looking at, if I can even see the intersection point. And it looks like I definitely can. It's right there. And I know from basic function sense, just an idea of how fast this cubic term is growing, that this thing's probably not coming back down to cross this line anywhere else. In fact, as we go to the right here, I mean, these terms are both positive, so this thing is just going to keep growing. There's nothing that can pull it back down. So this is our only intersection point. Let me do second trace, intersect, to find that intersection point. So let me do enter, enter, enter 3 times, and that intersects at about x equals 0.165. which means that that's actually the y value that solves this equation here. So if they intersect at about y equals 0.165, then if I want to write a horizontal tangent line equation, I'm just going to write y equals that number there. That is the equation for our horizontal line. All right, so let's also check the case where y equals 2. So this is a solution right off the bat because you have y equals a constant, but let's just plug it back into the original equation to make sure this thing actually works out. So if I plug 2 in here, I've got, let's see, 2 times 2 cubed, which is 16. And then plugging it in the next one, I've got 6x squared times 2, so 12x squared. Minus, we have a 12x squared there. Plus 6 times 2 is 12, and all of that equals 1, hopefully. So let's see here. We've got these x squareds canceling out. We have 16 plus 12, which is 28 on the left. We still have 1 on the right. The trouble is that 28 does not actually equal 1. So this is an extraneous solution here. It doesn't actually work out algebraically when you plug it back in. So then our only answer is the line y equals 0.165. For this last part of the problem, the line through the origin with slope -1 is tangent to the curve at point P. Find the x and y coordinate of point P. All right, so basically trying to find the tangent line for this thing that has a slope of -1. Well, one way to think about this is that our derivative, this thing right here that we saw in the earlier part, has to have a value of -1. Because if we're looking for the tangent line with a slope of -1, that means at the point of tangency here, the original function also has a slope of -1. So we need this to be equal -1. And there isn't really much we can do here algebraically. I mean, if you don't like the fraction, you could multiply by x squared plus y squared plus 1 to get -x squared minus y squared minus 1 on the other side. So we've got rid of the fraction, but there isn't really a whole lot else. You can't even really isolate x or y in this. So we need another equation, some way of substituting out an x or a y. Well, the key on this one is that they said the line through the origin with slope -1. Well, we actually know the equation of this line. Thinking about this in terms of y equals mx plus b, if you have a slope of -1, your m value is -1. If you're going through the origin, your b value, your y-intercept, is 0. This is none other than the line y equals -1x plus 0, or just simply -x. And this is actually an equation that we can use to help solve this equation. We know that y is equivalent to -x. So wherever I see y in this equation, and now, by the way, this is only equivalent at this magical 1 point of tangency, but wherever I see y in this equation, I can substitute -x. So I've got 4x minus 2x times -x equals -x squared minus -x squared minus 1. And let's clean this up now that we only have a single variable and try to solve it. Now, you are allowed to use the calculator, so this is something you could solve much like we did that last part of the problem. Or there's actually a way to do this without the calculator. Either way, cleaning this up, we've got a 4x over here. There's no other x terms anywhere, so that's going to stay where it is. This is going to be -2x squared. Over here, we also have a -2x squared. Actually, over here, this is positive 2x squared. This is a -2x squared over here. So adding that over here, we have 4x plus 4x squared, and then all of that equals -1. Now, if you don't want to do this on the calculator, you could move everything over to the left side and try factoring. So if we do that, we see we've actually got a perfect square sandwich here. This can be factored into 2x plus 1 quantity squared. And if you multiply that out just to double check, 2 times x times 1 does give you that middle term of 4x. So we're good here. So now if this equals 0, just adding 1 or subtracting 1 and dividing by 2, we have an x value of negative 1/2 that zeroes this out. If x is negative 1/2, what's the y value? Well, we can use this tangent line here because at the point of tangency, this thing is accurate. So y is going to equal negative 1/2 or positive 1/2. So then this is the x and y coordinate of our point.